Hey everybody. So Dr. Will Newton has a really nice video that he prepared when he put this course together on the scale of the universe and things like that. It's a nice PowerPoint presentation, and I'm going to go ahead and leave that up there because I like it, but I wanted to show you this very nice spreadsheet that I found for how you can sort of scale things within the solar system and distances to nearest stars. And then I'm going to go through how I usually explain it to students and use what works best for you. So what this spreadsheet lets you do is to pick a standard object. And so for right now, I'm going to do Earth to the Sun. And say that you want to do an exercise where you're going to have your students go out to the football field and kind of lay out some objects in the solar system, or at least just think about it and write about it maybe. So we're going to say our standard size is 100 yards. So we're scaling things such that Earth to the Sun has a distance of 100 yards. And so then on that scale, the Earth is 0.3 inches in diameter. So something like a marble, maybe, smallish marble. Distance from the Earth to the Sun, 100 yards. And then, so then the moon's diameter on that scale is about 0.1 inches, so maybe a BB or something. And it is 9 inches away, right? So students could actually lay that out, right? Marble, moon, 10 inches apart. Marble and a BB 10 inches apart. And then the sun diameter is about 33 inches. So beach ball size, something like that. And that's going to be at the other end of the field. And then the distance from Mercury to the sun, that's going to scale to 38 yards. So you can put something the size of Mercury, which is about 0.12 inches. And students can then say, oh, the moon is basically the size of Mercury, right? We have, 0.08 inches for the moon, 0.12 inches. So we can really represent that with the same thing. Those are basically the same size. The moon's a lot denser, but you get the idea. And so put that on the 40-yard line where the Earth is on the 100-yard line. Venus is going to have a diameter of about 0.3 inches. And we notice that that's basically the same as the Earth. So we can use the same size marble for that. And then the distance from Venus to the Sun, well, now Venus is on the 72-yard line. So Mercury on the 40-yard line, Venus on the 70-yard line, Earth on the 100-yard line. Then Mars is going to have a size of 0.16, so it's only about twice as big as the moon, and half the size of the Earth. And then the distance, 152 yards. So, where is that, right? So this is one of the things I like to do is to sort of say how, sort of scale things and then give local landmarks, right? So, use your school, your library, football field, distances, right, that the students can visualize. And I think that helps quite a bit. All right, so on this scale where Earth to the Sun is 100 yards, so when we go out to Jupiter, that is 500 yards, right? That's pretty far. We get out to Saturn, distance to Saturn, and we're at 1,000 yards, right? So at this point, we're kind of getting close to a good fraction of a mile. And then, so Neptune and then Pluto, whichever one of these you want to use, right? So 1.7 miles, 2.24 miles. Just to kind of show how the universe is laid out. So maybe you want to fit the entire solar system onto the football field. So let's just pick, let's see, do we have that? Yeah, we do. So we're going to do Pluto to the Sun, make that 100 yards. And so now on that scale, the Earth, look how tiny the Earth is, 0.01 inches. Earth to the Sun, right, it's not even listed here, so it's 2.53 yards. So we've got the Sun, which is going to have a diameter of less than 1 inch, right? So a good-sized grape or something, maybe a ping pong ball, give or take. Put that on the 0-yard line. Earth is going to be on the 3-yard line, 2.5 yards. Mercury is, let's see, where's Mercury to the Sun? So that's about 1 yard. And so then Jupiter, Mars is on about the 4-yard line. Jupiter is on the 13-yard line, Saturn on the 24-yard line, and Uranus on the 48-yard line, right? So this really shows how very spread out the outer solar system is. One thing that you might do if you were to do this exercise would be to say, okay, so you have the students realize that the sizes of the objects are just super tiny, right? So on this scale, the size of Jupiter is 0.1 inches, right? So it's tiny, right? So we can't really represent both the scale of the solar system and the sizes of the things, of the planets with the same scale. What we could do is we could do two different scales, right? Because this will at least give us relative scales. So we could do the sizes of the planets maybe 100 times the distance scale for the solar system or something like that. All right, so what I like to do when I give a standard talk or I talk to students is I like to say, if the Earth is the size of, I'm going to change this to 10 here. So if the Earth is the size of a softball, right, something nice and easy to visualize. So softball, grapefruit, something like that. So then, so the Earth diameter, size of a softball. So on that scale, right, and this is something that you can use with your students, then the distance from the Earth to the Moon is about 300 inches, which is Earth to the Moon, 300 centimeters. So that's 3 meters. And just notice that we can change this to meters and things like that. And so there we go, 3 meters. And so on this scale, the Moon is about 10 feet away, right? 3 meters, 10 feet. And the size of the Moon is about 1 inch, right? So I usually say softball, ping pong ball, right? And so that's how far humans have traveled, right? That's how far actual human beings have traveled. And so then on that scale, the distance from the Earth to the Sun is about 0.73 miles. So pick a local landmark from your classroom that is about a mile away. And that's going to be the Sun. And then the size of the Sun is, and let's convert this to meters as well. And so the size of the Sun is then about 10 meters, so about 30 feet. And so if you've been to our planetarium dome, close enough, call that 30 feet, right? So, or a building that's 3 stories tall, say, fit a ball into that building, that's the size of the Sun, and it's a mile away. And then you can kind of look at the distances to the other planets. So Jupiter on that scale is about 44 inches, where the Earth, again, had a diameter of about 4 inches, right? So Jupiter, about 100 times the diameter of the Earth. You can fit 1 million Earths into Jupiter, that kind of thing. And then the distance is that many yards. Let me convert that to meters. And so, 6 kilometers, we can put that into, can we put that into miles? No, I guess there we go. So we can put it into miles, so about 4 miles away. Right. Just something nice to play with. Distance from Pluto to the Sun, about 28 miles, right? So from here to Commerce, if we're in Commerce teaching this, we might say, hey, so, this Pluto is kind of in Rockwall, right? And a little bit further from that is how far our robot spacecraft have gone, right? So about 50% further than that. So our robot spacecraft on this scale, where Earth is the size of a softball, have made it to downtown Dallas, right? And now what you can do, what I like to do for the next step, is I like to say, well, now let's scale things down by a factor of 100, and now we're going to make the Sun the size of a softball, and then say, so how far is it, right? So we've scaled things down by a factor of 100. How far is it to the nearest star? And so for that, let's see, do we have Proxima Centauri here? Nope, I guess we don't. But so that comes out to be about 3,000 miles, okay? So we have to go up into Maine or northern Canada or something like that when the Sun is the size of a softball. So the distances between stars are very, very big, all right? then the next thing that you can do is to say, okay, so now the galaxy is made up of about 100 billion stars. And in fact, if you take some nice beach sand and you put that into a boot box, you get about 100 billion grains of sand. To distribute those, where the radius of the grains relative to the spacings between them is the same as stars in the galaxy, that boot box of sand has to extend from here to the moon. You have to spread that out into a disk that extends from here to the moon. So again, stars very far apart relative to their sizes. And in about 4 billion years or so, our galaxy is going to have a collision with the Andromeda galaxy. We don't know how head-on it's going to be, but at some level it's going to happen. So 100 billion stars in our galaxy, 100 billion stars in the Andromeda galaxy, but because there's so much space between stars, those two things are just going to run right through each other. And I forgot when I was going through, so I'm just going to patch this in. We're not going for studio quality here, we're just going for pretty good. So to follow up on the galaxy thing, so now if a galaxy is the size of a dinner plate, then how many galaxies are in our classroom? And students, right, they've been primed on how far apart stars are, and so they say, to the moon, right? But in fact, galaxies are very close relative to their sizes. So, in your classroom, you hold your hands up the size of a dinner plate. In fact, there's a lot of galaxies on that scale that are inside your room. The interaction of galaxies is very important to the evolution of galaxies, as we're going to see later in this course. Now back to the story. Your homework problem, one of your homework problems is to say, all right, so if I want to travel to the nearest star, typical distance between stars is about 5 parsecs, 5 light years. So if we go at 10% the speed of light, that's going to take us 50 years, right? So it's going to take light 5 years. If we're going 10% that speed, it's going to take us 50 years. And then if we travel in a spaceship as small as a 747, how much kinetic energy is that? And what you're going to find is that that amount of kinetic energy is comparable to the global output of the planet for one entire year. So I want you to actually kind of find that information and confirm that I got my numbers right. And if I don't, please do let me know, because I've been telling this story for quite a while. But just to emphasize to students, right, that it's not like we see in movies. Stars are very far apart. It's going to take a long time to get there if we ever even set out on that. And, a 747 is a pretty small ship to stay in for 50 years. And that's just the kinetic energy to get it to 10% the speed of light. And extension cords just aren't that long. All right, so I'm going to leave it there, kind of have some fun with this spreadsheet. I'm not sure where this might fit in the discussion forums if you kind of want to talk about how you might use this with your students, but if you want to make that one of your postings, go for it. All right, we'll see you soon. Bye.